what we're doing in Unit 4. So those applications at the end of Chapter 6. So 6, 7, and 6, 8 are the sections. So kind of do a quick review of what we talked about last time. Because we did examples involving exponential and logarithm functions. So for the exponential examples, we did exponential growth and exponential decay. And that was using essentially the same formula, our PERT formula. If R is a number bigger than 0, it's an example of growth. And then R less than 0 is an example of decay. So you can call it decline, decay, whatever you want to call it there. With growth, we talked about doubling time. Every single exponential function of this form has a corresponding doubling time. And that's really, as I mentioned last time, what makes an exponential function. Kind of the definition of an exponential function. And for decay, we have what's called a half-life. So these problems now are going to come in a couple different varieties. The half-life, sometimes you're going to be given the half-life, then you have to calculate R. Sometimes you're given R and you want to calculate the half-life. So it all depends on the application that you're doing there. So if you do an example here where you start with 125 grams of a drug in a system, and the system is going to decay that drug 30% every hour. And I want to ask you, what's the half-life of this drug in your system? So when you talk about the half-life here, you're saying, how long will it take that 125 grams to decrease by half? So we need this equation. Once we know that equation, we could find the half-life. So we'll start with our 125. This equation uses e to the RT. A 30% per hour decay rate, we might want to start with the other representation, a times b to the power of x, or the power of t in this case. Because we're decaying, r is equal to negative 0.3. So you can use this formula if you want to, or you can change it to the e to the RT formula, either way you want to do it. In order to get the half-life, you're going to need to replace a with half of the original amount, 125. Half of 125 is 62.5. So I'm going to keep it as a 0.7. You can change it over to, like I said, e to the RT if you want to. But this is going to be the same calculation you do every time for half-life. If you divide both sides by the initial amount, what is 62.5 divided by 125? 1/2. Because in order to use the definition, you need to have base, exponent, answer. So I'm going to continue to use logarithm base 0.7 here. You can change it, like I said, to e if you want to. But we're going to convert this one to logarithmic form. So it's logarithm base 0.7 of 1/2 is equal to t. So that's how long it'll take for half the original amount to disappear. So let me get to you the quick calculation here. Logarithm base 0.7 of 1/2. 1.94. And 1.943, we're measuring it in hours. So after almost 2 hours, your initial amount of 125 has gone down to 62.5. So something else the half-life tells us here is every 2 hours, whatever's in your system will have decreased by half. We start with this much, decreases by half in 2 hours. Then after the next 2 hours, decreases by another half, then by another half, then by another half. So it goes down 30% every hour. You could also say it goes down by half every 2 hours. So you now have another way of kind of saying what's happening to this drug in my system. The other thing you may remember about these types of functions, if you look at a graph, it's going to look like this, which means no matter what the time is, there's always going to be a little bit of that drug in your system because there's a horizontal asymptote. But I'm guessing that after a while, it's just a little bit, it wouldn't affect you as much as the initial amount or half the initial amount or half of that half. So. All right, there are a couple other specific examples of exponential growth and decay. We're not going to go over them in detail here, but I'm just going to kind of outline what they are. There's something called carbon-14 dating. So this is a type of example where if you have, for example, a fossil that's been dug up, you try to figure out how much carbon-14 is measured in this fossil, because after you die, pass away, you assume you have 100% to start, and as time goes on, you lose carbon-14 in your fossils in the bones. So for this one here, you need to know what the half-life is of carbon-14, and that's given to you. It's 5,730 years. So because of this, we can use a similar calculation as we did down here and come up with the actual formula that's going to give us what percent of carbon-14 remains after a certain number of years. And the formula looks like this. This is the value for R. I think our book uses K, but R and K are the usual numbers used for these growth constants. This number is about 0.00012. So this is your formula to calculate how much carbon-14 is remaining in your object after T years. So this is knowing what the half-life is, coming up with that value for the constant. So you can think of this as like a continuous decay rate of 0.0121%. If you want to change that to a percentage. So that's another example that uses essentially that formula. The other one that's mentioned in this book is Newton's law of cooling. It's actually Newton's law of cooling or heating, depending on your application. So if you're going to be taking calculus, we talked about this more in calculus, also in differential equations. The law actually says if you have something that is at a warmer temperature and you put it in surroundings at a lower temperature, that higher temperature will eventually decrease down to it's called the ambient temperature, the temperature of your surroundings. So that seems to make sense. You put something, take something out of the oven, put it on the counter, it's going to cool. The rate at which it cools is modeled by an exponential function. So this is another one where you don't need to know where the formula actually comes from, but you want to be able to use the formula. So there are three variables to use here. The three variables are temperature of the surroundings, the initial temperature, and then once again, you have some sort of constant. It's actually a decay constant because your temperatures would be going down if it was cooling, and then it would be a growth constant if it was going up. So T sub S are the surrounding temperatures. And then A is actually calculated. It's not the initial temperature. It's actually the difference between the initial temperature and the surrounding temperature. So that can be calculated. And then you need to know one other point in order to calculate K. So what's happening with these Newton's law of cooling problems is you're actually going to say, here is your surrounding temperature. If your temperature starts at a number above that, it's going to cool and eventually get down to the surrounding temperature. If you start at a number below that, it's going to do the opposite. It's going to go up from there. So it's like an exponential function that's been shifted up or down a certain number of units. I like to think up because we want our temperatures to be positive. I realize we are getting close to winter, so maybe that's not accurate anymore. But starting at a higher temperature, decreasing down to the surrounding temperature. So think about something taken out of the oven, pouring yourself a cup of hot beverage, or taking something out of the freezer and having it warm to room temperature, for example. All right, these are all good. I really like these applications. It's mentioned in the book that the carbon-14, this is a real rough estimate. It all depends on how precise your measurement is, how much carbon is actually left in the fossil. So as you are able to get a better reading on that, it'll give you a better approximation to the year. All right, give you a chance to do a screenshot here, because we're going to go talk quickly about those logarithmic models that we did last time. Oops, what happened there? And then do one new model, and then talk about how our calculator is going to work here. So let me clear this off. So just a quick review of the logarithmic models. We did the pH of a substance, and just write down the formula that we talked about last time. We did the earthquake intensity. And then our book uses this, it's called the moment magnitude scale. And the only difference between that and the Richter scale is the 2/3 out front. So I'm just re-quoting the formulas we talked about last time. This is the energy released by essentially the smallest earthquake we can actually feel. And then this is the energy released by the measured earthquake. And then we have decimal levels. And we had talked last time about why we need logarithms, or why logarithms were introduced to calculating each of these quantities. So here I sub 0 is about 10 to the negative 12. I think that's watts per square meter. So once again, very, very small number. So wide range of values we're talking about there. Wide range of energy levels for earthquakes. Wide range of levels for hydrogen ion concentration. So you'll not have to be, have to memorize these formulas. I would just like you to work with them. You'll be given the formula. And then now that we know how to solve these equations, given this number, can you calculate the answer? Given the answer, can you calculate this number, for example? And then the hydrogen ion concentration was in moles per liter. So if you think about numbers on a logarithmic scale, if this is our usual number line, 0 to 10, we just go from 0 to 1, increase of 1, 1 to 4, increase of 3, 5 to 7, increase of 2. But this is a logarithmic scale. If you go from 0 to 1, 0 is actually not the number we're representing here. It's the logarithm of that number. So to actually get what is x, this is actually the same as 1. 1 is the same as doing logarithm base 10 of x is equal to 1, which means that answer is 10. So we identify essentially the exponent. That's what logarithms are, they're exponents. So as you go up from 0 to 1 to 2 on the logarithmic scale, these are the actual numbers. So every step on the logarithmic scale, increase of not 1, but 10 times the previous number. And that's how we measure these things. It gives us a way to take something that has a very wide range and represent it in a much shorter range. So those are our logarithmic models. So I'm going to show you a few scatter plots that we have already done, because we're going to do in the last section scatter plots for exponential and logarithm functions and introduce one new function. So if you did or didn't do CTP or ATP number 1, you had a graph that kind of looked like this. If you did actually that's a second one, sorry. If you did the third one, you had a graph that kind of looked like this. If you did the fourth one, you had a graph that kind of looked like this. And if you are going to be doing the fifth one, spoiler alert, one of your graphs is going to look like that, and the other one's going to look like this. So by looking at the scatter plot, what kind of function is going to be a good model for this? This is a good example of a linear function, excuse me, quadratic function here. This one goes kind of up, flattens out for a little bit, continues to go up. That's more like a cubic. And these are both exponential. One is growth, one is decay. But we have many different types of functions that increase. Linear functions increase. Cubic functions increase. This type of exponential function increases. There is one other model that also increases that we're introducing in this unit, and that's the logarithm function. So if you have an increase, but it's a pretty slow increase, a logarithm function is a better model for that. So rapid growth, exponential growth, if you want to call it that, modeled by this function right here. And we just used the usual A times B to the power of X for that one. For the logarithm model, it also uses, actually it also, didn't mean to say that. This one uses the natural logarithm. This one is base B. This one is logarithm base E. Now you can convert that to another logarithm if you want to, but that's what our calculator does. I'm pretty sure Desmos does the same thing. You might want to check that. Well, let me show you on the calculator the difference between the two. All right, so let's go to stat. Okay, here's a set of data. So 1 to 10, look how the numbers are increasing. We go from 2.4, in the end, we end up at 12.383. So they're going up. Are they going up, you think, like this? Or are they looking more like this? So two types of functions we're trying to look at here for a model. So exponential function or a logarithm function. So if we do a scatter plot here, let me make sure we're not getting bogged down by these old examples. Okay, there we go. So if we do a scatter plot here, turn our plot on, and let's set up our window. So let's start at 0 and go up to 12, so we can see the outputs there. And then for the y values, let's go from 0 to 25 or 26 should work there. Go up by 2. So with these problems, look at a scatter plot, and then you can decide whether you think an exponential function or a logarithm function is a better model. So what do you think about this one? It looks like it is increasing and starting to take off. That would suggest an exponential function model. So all you have to do is go back to stat, over to calculate, find your exponential regression, and those are your values for A and B. So A is about 2, and then B is about 1.199, we'll call it 1.2. So you may have noticed back on the y equals screen, there it is. That is the exponential model. When you put both of those together, that looks like it's a pretty good fit. Pretty good fit. We could also do a logarithmic model. And this is the nice thing about having all those numbers into the calculator. You can call up any model you want. Do a little mix and match here. Number 9 on the calculator is ln regression, which is the natural logarithm function. So call it up. Gets you your two values for A and B. So notice that A is 0.25 and B is about almost 4, 3.96. I also have that function typed in here. So let's plot those two together And then you can decide which one looked like it was a better fit. Now you think you can tell right away, once we get here, these numbers start to increase at a more rapid pace than the function is showing us here. So the other models seem to go through or close to all the other points. This one is either above or below, not very many of these points where it goes through. So you're probably guessing exponential function is a better model for that one. I would agree. So this would be what you just find, write down 2 for A, 1.2 for B. You can come up with the model for this, but you would probably say, here's what the model equation looks like. Here's what the graph looks like with respect to the scatter plot. Doesn't look like it's a good fit. So there's one other type of example you're going to find in these last 2 sections. And let's see if I can squeeze it in here. There is a situation in which your scatter plot looks like this. So you kind of look at these 2 functions here, and if you kind of put them together, you get a graph that looks like this. This is sometimes called the logistic or the limited growth model. There are situations in which the beginnings of an application look like an exponential function. So going up, we talk about a value of R, things like that. But over time, for whatever reason, your inputs are still increasing, but they're slowing down, and they actually start getting closer and closer to a number. And that's what we call the limited growth. It can only go up to a certain number. So think about a population that has limited resources, or some type of virus going through a population. There's only a certain number of people it can infect. This is what the model is going to look like. All we're going to do with this model, we spend a lot of time in calculus, other classes deriving the model, talking about growth rates in the beginning, growth rates in the end. There's this kind of point in the middle where it's growing at its fastest rate. So on this side, it's going up, but on this side, it's going down. Here's the equation. So this is the limited growth function. C is the top number. And then there are 2 other constants to determine A and B. And it's a little less obvious is the right word. In here, in this problem, A is the y-intercept of the function you're starting with. The only thing that's kind of obvious here is C. C is as big as your outputs are going to be. As T gets bigger, this expression gets closer to 0. If this is getting closer to 0, A times a number close to 0 is also close to 0. So you actually have C over 1. So your horizontal asymptote for these problems is going to be y equals C. This is sometimes called the carrying capacity. So some of the problems in section 6.7 and 6.8 have you working with this function. So all we're going to do is work with the function, put in some inputs, calculate some outputs, get a graph. All you got to do is type in the equation as you see it, and then possibly go to the calculator and come up with a model. So how do you decide whether an exponential unlimited growth example is a better model than the logistic or limited growth model? It all depends on what your scatter plot looks like. So if you have a set of data, let's see if we have time to do this or not. I'm going to type these in real quickly and then give you a chance to do a screenshot if we want to. Okay, so I'm going to go to L3 and L4. So for L3, I'm going to type in 1, 3, oops, not 2, 5, 7, and 9. And then my outputs are going to be 8.7, 15.4, 20.7, 23.3, and then 24.6. So here's one, if you look at the data is increasing. Oops, that one I typed in wrong. That should be 15.4, sorry. I was gonna say it's going up, but not that fast. It's going up quickly in the beginning, but once you get past 20.7, it's going up at a much slower pace. So that's an example in which a logistic model might work a little bit better. So if we do a kind of a quick scatter plot here, this is gonna be kind of messy because the other one's on there. I thought that's going to show up. What happened there? Oh, I forgot to ask it to do L3 and L4. Do that real fast. Okay, so here's the scatter plot. So it's going up, but then you can see it's kind of leveling off. So it's not a logarithmic function because logarithm functions don't have horizontal asymptotes. So you can call up the logistic model here if you want to do a model. And then it's going to give you, actually do L3 and L4 here. Okay, so notice the format. It gives you A, gives you B, gives you C. So C is your maximum output. Based on the model, the outputs will not go above 25. And then A and B have something to do with the initial numbers and how the rate of growth changes throughout the problem. All right, so sorry about going over a little bit here. I did want to make sure you saw an example of that because that's going to be part of your homework for tonight. So any other questions for now? Anything else? If you have other questions about the quiz, send me a message. And if you have any questions about the weekly homework, do the same. On Monday, we will start a new unit, Unit 5. We've got 2 more units to do. But next week's quiz is going to cover the last part of Unit 4. All right, if you have no other questions, have a great weekend. Good high temperatures. This might be your last hurrah. So last hurrah for fall, I should say. So have a good weekend, everybody.
Good weekend.
You too, Shay.